Hello there. Today, we're going to pull back the curtain and take a peek into the quiet, hidden world that lives inside the tools we use to write software. We're going to explore the secret life of our code, and our guide on this little journey is a really powerful technique called data flow analysis.
You've probably had this happen, right? You're just typing away, minding your own business, and then a little squiggle appears under a variable, warning you about something. It almost feels like magic. How in the world does your editor already know something's wrong? Well, that's the exact question we're going to gently unpack today.
All right, let's dive in. It all starts with a very simple, quiet question. But the answer? Well, the answer reveals something pretty profound about how we manage the unbelievable complexity of the software we build every day.
I mean, let's be real. The fundamental challenge is that modern software is just staggeringly complex. We're talking millions, sometimes hundreds of millions of lines of code, with an almost infinite number of paths the program could take when it's running.
And this quote from the textbook on compilers really puts it all into perspective. Think about that. We're not just building apps or websites, we're building some of the most intricate systems humanity has ever created. And with all that intricacy comes a huge challenge. How do you make sure these things actually work and are secure?
So what's the big deal? What are the actual consequences of all this complexity? Why does our code need this kind of invisible helping hand in the first place? Well, all that complexity is the perfect hiding place for mistakes. Things like buffer overflows, a classic and really dangerous security flaw, can just lurk there, totally unseen. We're talking about the kinds of deep, nasty errors that lead to system crashes, corrupted data, and serious security breaches. Trying to find every single one of those by hand, it's pretty much impossible. And that brings us right back to our original question. If we can't possibly trace every potential outcome in our own heads, how on earth do our tools manage to do it for us and do it automatically?
The answer lies in a technique that we can think of as a kind of code detective. It's like a quiet investigator that examines our code, checks out every lead, and follows every possibility, all before the code even gets a chance to run. The official name for this detective is data flow analysis. And really, it's a whole family of techniques for figuring out how data moves through a program. But the absolute crucial point, the thing that makes it all work, is that it does this statically. That just means it analyzes the code without actually running it. It just reads it. And that is how our tools can spot problems before we even hit compile.
Okay, so how does this detective actually do its job? It sounds incredibly complicated, right? But the core strategy, the real genius of it, is built on just a few simple, really elegant ideas. So let's break that process down. We're not going to get lost in all the heavy-duty math behind it. Instead, we're just going to focus on the beautiful, intuitive logic of how it all works. First things first, the detective has to map out the scene of the crime. The analysis builds something called a flow graph, which is basically a roadmap of all the possible paths the program could follow. An if statement, that's a fork in the road. A for loop, that's kind of like a traffic circle you might go around a few times.
Now, here's what's so clever. The analysis doesn't try to understand everything about the program all at once. That would be overwhelming. Instead, it asks very specific, targeted questions. For example, one type of analysis might just ask, for this variable right here, on this line, where are all the possible places in the code that its value could have come from? This super-focused approach is what makes it so powerful. It builds a complete picture one tiny piece at a time. So, the analysis then walks down every single one of those paths on the map, gathering clues related to its specific question. And when two different paths merge back together, like after an if-else block ends, it has to combine the clues it found. It has to look at the info from both the if branch and the else branch and create a summary of what could be true now that they're back together.
But what happens when the detective isn't 100% sure? What if a path is theoretically possible, but it seems really, really unlikely to ever happen in the real world? Well, to be useful, the analysis has to always play it safe. And this gets to the heart of it, the principle of conservatism. The analysis always asks what might happen. It never tries to predict what will happen. So it might miss a chance to make the code a tiny bit faster, but it will never allow a change that could actually break the program. It's way better to be a little cautious than to be wrong. This is one of the fundamental trade-offs in this field. Correctness always wins over performance. So after all this careful investigation, all the mapping and the questioning, what do we actually get? What's in the detective's final report?
Well, the results of data flow analysis are the secret sauce for so many of the tools we rely on. This is what helps compilers optimize our code to make it run faster. It's what enables that static error checking we see in our IDEs, the little squiggles. And it's what powers the security tools that find vulnerabilities by tracking where sketchy data is coming from. Honestly, it's what makes modern software development even possible.
So the next time you see that little warning pop up in your editor, you'll know it isn't magic. It's actually the result of this deep, careful process that's always working in the background, on your behalf.
It's this tireless little detective, constantly analyzing the flow of data, making connections, and checking every possibility, all to help us build better, safer, and more reliable software. It's like a silent partner in our craft, a quiet intelligence helping us manage this incredible complexity.
And these ideas didn't just come out of nowhere. They come from decades of computer science research captured in foundational books like this one. It's the science of how to build a compiler. But as we've seen, its impact goes so much further than that. This work is the reason we have the amazing tools we get to use every single day.
And maybe that's the real takeaway here. It's not just about the mechanics of the analysis, but about having a deeper appreciation for the silent, thoughtful engineering that supports everything we do. It turns a ridiculously complex craft into something just a little more manageable. So next time you write a line of code, maybe just take a second to appreciate that quiet intelligence that's always there, working right alongside you. Thanks so much for joining me.